So crystallization we're defining as when you have an ordered structure with some specific distance between chains. When you put in sufficient energy to overcome those bonding forces, we have melting, and simply the chains become disordered and your sample will flow. Where that temperature occurs depends on factors just like TG. Symmetry is one, because in order to build up into an ordered structure, your chains need to have a lot of symmetry so they can fit together nicely. Intermolecular bonding or hydrogen bonding can also have an effect. Branching can be important because, again, if you have bulky side chains or branches, that may interfere with the ability of your chains to order, and your chain length or molecular weight can be important as well. So here we see a couple of examples of those effects. On the left, we have nylon 6,6. And in these chains, we have carbonyl oxygens that really like to line up with the amine hydrogens and form hydrogen bonding. So that's a driving force for these chains to line up next to each other and form crystals. So nylon 6,6 is usually found in a crystalline form. Tacticity is another effect, and that's related to stereochemistry or symmetry of your molecule. The symbiotic polystyrene here in the middle has phenylrenes that are alternating on different sides of the chain. And you can imagine that if another chain came and lined up with this, they would fit together very nicely. Atactic polystyrene, on the other hand, has those phenylrenes just randomly along its chain, and therefore it would be very difficult to pack these together closely. And indeed, atactic polystyrene is typically amorphous. So now we've kind of gone over TG and TM. What does this mean for our polymer systems? Well, this is a generic modulus temperature graph where we have modulus along the y-axis and temperature on the x. We see that as we begin heating our sample, we see a drop in the modulus, and that's going to correspond to our glass transition.